Well, good morning, everyone, and welcome to the State of Utah Energy Storage Summer Webinar Series presented by the Department of Energy Office of Electricity Energy Storage Program in collaboration with the Utah Governor's Office of Energy Development, Sandia National Laboratories, Pacific Northwest National Laboratories, Mustang Prairie Energy, Quanta Technology, and the University of Utah's Utah Smart Energy Laboratory. My name is Kevin Brooks. I am the Energy Analytics Manager with the Utah Governor's Office of Energy Development. Today's session is the last in our webinar series, and will cover energy storage and grid resilience. Today's session is also being recorded, so we ask that you remain muted throughout the presentation and save all questions until our question and answer and discussion session at the end of today's webinar from 11:50 to noon. At that time, please feel free to unmute yourself to ask your question, or you can send it to me through the chat function, and I'm happy to ask on your behalf. And so with that, I will move on to our introduction and recap of the series from Dr. Imre Gyuk, Director of the Department of Energy Office of Electricity Energy Storage Program, which is responsible for providing funding for this series. And so for the past 2 decades, Dr. Gyuk has directed the Electrical Energy Storage Research Program in the Office of Electricity, developing a wide portfolio of storage technologies for a broad spectrum of applications. And he is an internationally recognized leader in the energy storage field. So Dr. Gyuk, welcome today.
Well, good morning. It's a pleasure to be back in Utah again. And as Kevin mentioned, this is the 6th and last of our sessions on energy storage. And it's been a bit of a voyage. We've had an introduction to energy storage, the materials and technologies involved. We've gone on to the analytics, the cost-benefit calculations that underlie storage when applied. That has brought us to case studies, both very large and smaller ones. And then we have had presentations on finance, because finance is necessary if anything is going to work. But in order to get there, you need policy. And so we had various aspects of policy, and a very good presentation by Representative Handy, much appreciated. So today we're going to conclude by considering resilience. And resilience is both an issue for the present and even more so for the future. For the future, for the present, we have, well, all kinds of disasters. They could be localized, or they could be fairly widespread. Hurricanes, earthquakes, wildfires. We've all had them in the last 2 years or so. And of course, now we have a pandemic that we're trying to deal with. In the future, we are looking forward to increasing deployment of alternative fuels, renewable fuels, wind and solar, and to some degree also biofuels and geothermal. And these are by and large variable, and we have to, in order to accommodate them, we will need large amounts of storage. And we will need to build a grid that is much more resilient than the current one. The analytics for building this resiliency is a hard topic. It's difficult. And so the presentations you will get today will probably be among the hardest ones that we've had in the series. But we will hear from Masood Parvania from the University of Utah. We will hear from Howard Passell from Sandia, who will try to make this a little bit more simple. And then finally from Ralph Masiello, who has been in this field for a considerable time and is now with Quanta. And he will talk about the storage as a replacement for either generation or transmission or distribution upgrades. So, thank you for your continued interest in energy storage, which is of crucial importance for our energy future. Thank you and enjoy the presentations.
Thank you, Dr. Gyuk, for the introduction and recap of the series there. Moving forward, I would like to introduce our keynote for today. Dr. Masood Parvania is the director of the Utah Smart Energy Laboratory and associate professor and associate chair for research and advancement of the Department of Electrical and Computer Engineering at the University of Utah. His research interests include the operation, economics, and resilience of power and energy systems and modeling and operation of independent critical infrastructures. Dr. Parvania serves as an associate editor of the IEEE Transactions on Smart Grid, the IEEE Power Engineering Letters, and the IET Renewable Power Generation. He is the chair of the IEEE Power and Energy Society Utah chapter, the chair of the IEEE PES Bulk Power Systems Operation Subcommittee, and the vice chair of the IEEE PES Risk, Reliability, and Probability Applications Subcommittee. So welcome, Dr. Parvania.
Thank you very much, Kevin, for the introduction. So, do you hear me now?
Yes, I can hear you loud and clear.
Great. Thank you. Thank you for the introduction. Good morning, everybody. I would like to first thank Dr. Gyuk for his leadership on energy storage and also the introduction of the webinar series that we have been having in the past 6 weeks. And thank you for your interest and listening to this webinar series, and I hope that this has been useful for you in the past 6 weeks, this webinar series about energy storage. So today I'm going to talk about the role of energy storage for enhancing the power grid resilience and the opportunities that exist for Utah to utilize energy storage for enhancing the grid resilience in Utah. So I would like to first start with the definition of resilience and what really resilience means. So resilience in the context of the power grid is the ability of the power grid to prepare for and adapt to changing conditions and withstand and recover rapidly from adverse events such as severe weather. As really is clear from this definition, the resilience is different from the power grid reliability that we have been concerned mostly about in the past many decades. Reliability is about ensuring the continued supply of electricity against random failures that we typically get in the power equipment, but resilience is about preparing and adapting and recovering as soon as possible from large-scale events such as severe weather. And in fact, in the past, decade, 2 decades mostly, and specifically in the past 10 years, the number and impact of weather-related electricity outages has been increasing all over the world, but specifically in the United States, with more than 80% of them initiated in distribution networks. This map from NOAA shows what they call $1 billion weather and climate disasters that refer to the events exceeding $1 billion in damage cost. This map shows specifically the number and location, the name and location, and the date of these $1 billion events in 2019. And in the table on the right shows the number of these events in the past 10 years, which have been 120 and for an average of around 12 events every year in the past 10 years, which with the damage cost of more than $800 billion, an average of $80 billion every year, and more than 5,000 deaths. And this has been clearly an eye-opening statistics for the power grid, and as just like Dr. Gyuk said, this is probably going to increase in future. So what it means for the power grid is that we want to make sure that the power grid is going to be resilient against this increasing number of natural disaster that is affecting a large geographical area. So in Utah, we have had our own share of these natural disasters, but of course in a smaller scale and a different scale. We don't get a hurricane in Utah, of course, but Utah is known for the Wasatch Fault, where the urban area in Salt Lake Valley is. Wasatch Fault passes through this urban area, which has been active for more than 100,000 years. And we got the latest activity of this fault just happened like in March 18, just in the beginning of the pandemic. We also got this earthquake, which kind of like was got everybody by surprise. An earthquake of magnitude 5.7 happened in Utah, which caused like evacuation of the airport and caused power outage for more than 73,000 customers. And Rocky Mountain Power had to evacuate the control center and temporarily transfer the control center to Portland. And they acted very quickly and they were very prepared for that. But this is something that has happened, and but we were able to recover from this very quickly. And we get a lot of snowstorms in Utah, not necessarily in winter. In March 29 in 2019, we got a spring snowstorm, which was scattered around the large geographical area, caused 19,000 customers out of power, and which the reason was that there was like a heavy snow on the trees. The tree branches broke and fell on the power line and caused damage, which at some point took like more than 2 days to repair and restore power back to the customers. So the question that we are dealing now is that how energy storage is going to be helpful, and what is the role of energy storage to enhance the grid resilience. So energy storage can help energizing customers during grid outages by providing localized power supply. But in order to enable energy storage to play this role in the power grid, we need to modernize and automate the power grid, and specifically distribution system operation, in order to make sure that we are able to utilize energy storage rapidly after outages. So a toy example, I would call it, on a small feeder is shown in this figure in the left side of the slide, that shows For example, we get these outages in this tree distribution line, and what happens is that we lose the power for all the feeder because the circuit breaker acts and opens the feeder. And what we can do if we have the if we have energy storage at the end of the feeder, is while we are repairing these lines and while the customers are going to be in outage at the end of the feeder, by having energy storage and possibly other sources of energy at the end of the feeder, we can recover power back to the customers that are not otherwise going to have power during the outages. And this in terms of the, as I said, this requires modernizing and automating the grid, and potentially by having localized sources of energy, what we can do, we can prioritize critical loads that are, of course, are of highest importance to recover after outages. And make sure that we are enhancing resilience by reducing the energy not served during the outages. In Utah specifically, there are a lot of opportunities to take advantage of energy storage for enhancing the grid resilience in different sectors of the grid. Specifically in distribution grid, we have been working with Rocky Mountain Power Governor's Office of Energy Development and multiple partners all over the country in order to develop advanced resilience management system, or like what we call ARMS, that is funded by DOE and Utah's STEP program that has enabled installing a lot of these automation equipment all over the Utah, specifically close to the critical customers, in order to enable recovery of the customer and utilization of distributed energy resources for resilience. And Utah is host to like a lot of critical loads, like many other places, but specifically Utah is having a growing tech and medical industry that heavily relies on resilient and reliable supply of power. And in the past 5 years specifically, a lot of industries have been moving to Utah, and there is a huge opportunity to make sure that they are having access to reliable and resilient power, and definitely energy storage can play a great role on this. And we just heard like a few weeks back about the solar community, Electric community project that is specifically looking at utilizing energy storage in every apartment in that complex to provide local support for the residents, which would not only improve efficiency during the peak times, but also would play a critical role for enhancing the resilience of that community. And in Utah, we have we house 4 important military bases, including Hill Air Force Base, and it is very critical to ensure their reliability and resilience. There has been project going on to site renewable energy resources in these Utah bases, and I believe there is a huge role for energy storage in these bases. And we just heard a few weeks back about a large hydrogen energy storage project, which is a unique project in the country to enhance the resilience in the transmission level scale, which is a very large scale energy storage and seasonal energy storage. In terms of the research and development, my lab at Utah Smart Energy Lab at University of Utah, we have been involved in many on the research and development side of many of these projects in the past few years, specifically for integrating energy storage and enhancing cyber physical resilience, among many others. And explicitly, we have developed the cyber physical resilience test bed in University of Utah, which is very critical, which plays a very critical role to ensure that we are able to test and validate the application of these advanced technologies and software tools that we integrate on the grid first in a lab environment to make sure that they are going to operate properly on the grid environment before utilization. This test bed enables testing cybersecurity solutions that we develop, as well as new hardware and software technologies that are going to be utilized in the grid before utilization on the grid. First, we verify them on the in a lab environment. In addition, we have been supporting the education and workforce development in power and energy and in the resilience topics in the state. Specifically, we have been working with the Governor's Office of Energy Development, specifically with Kevin, in the past 2 years, and developed what we call Utah Power and Energy Carrier Expo, which provides the venue for the power industry to connect very closely with the students and with the future workforce to make sure that we support and we deliver the workforce that is needed to advance the technologies on the state. And this year specifically, University of Utah was going to host Resilience Week, which is a international conference on resilience technologies led by Idaho National Lab and involving many other national labs, including Sandia and specifically DOE. But this week, this conference, unfortunately, we had to turn it into a virtual conference. So it is going to be held, but virtually. But we may bring it back to Utah next year. So I invite all of you to look for this conference. There are many exciting talks and papers coming out, which is going to be held on October 19 to 22. So at the end, I would like to appreciate all of our partners and supporters, explicitly Dr. Gyuk, who has been supporting and funding our research in the past 2 years. We appreciate that and look forward to continue working with many partners in coming years for advancing power and energy technologies and resilience in Utah. Thank you.
Thank you, Masood, for providing the keynote introduction today. Moving on, we have an energy storage and resilience presentation from Dr. Howard Passell. Howard works in the Energy Storage Systems Department at Sandia National Laboratories in Albuquerque, New Mexico. His work focuses on energy storage, grid modernization, energy security, and decarbonization. Over 23 years at Sandia, he has worked on energy and water resource monitoring, modeling, management, capacity building, and policy-related projects at various scales in the United States, Central Asia, the Middle East, and North Africa. This included helping to lead Sandia's efforts in the Department of Energy's Solar America Cities initiative and developing energy conservation software and methodology for large institutions. He has worked on emerging national security issues associated with energy, water, food, ecosystems, and population, with an emphasis on the relationships between resource scarcity and human security. He earned his master's and doctoral degrees in conservation biology and hydrogeoecology at the University of New Mexico. His undergraduate studies were in classical literature and the liberal arts at St. John's College in Canavate, New Mexico, and the Ohio State University in Columbus, Ohio. So welcome, Howard. All right, Howard, I think you might be muted there.
Okay, sorry. Yes, indeed. Thank you very much, Kevin. So I'm going to leave my video on. Let me know, Kevin, if it seems to be slowing things down. And also by my video, you can see that the picture that Kevin had and the real me, the picture must have been taken some years ago. So So I'm going to talk about two related topics, related by the term resilience, really, but otherwise fairly separate. Energy storage and resilience, that is how resilience can contribute to, or how energy storage can contribute to resilience, and then also turn things around and talk about the resilience of energy storage. That is, how can we be sure that energy storage will be resilient to changes that happen in the environment and the marketplace and supply chains and so on. So thank you all for being here. So one of the criticisms of resilience studies now is that we have failed to define resilience well enough, and it strikes me that resilience is a lot like the term sustainability some years ago. It was bandied about a lot, but everybody complained that it was difficult to define. So I'm going to take a few slides just to talk about resilience, partly because it's really interesting to me, and maybe it'll be interesting to you. So this is a picture of a resilient system. So you have system performance on the y-axis, you have time on the x-axis, and you have the system oscillating up and down, but coming back to some kind of average behavior and never crashing, never exploding. And I would argue that complex adaptive systems, all of them oscillate. Now, I haven't studied all complex adaptive systems, but a few of them listed there at the bottom, they all oscillate. And I think that that's probably characteristic of all of these kinds of systems, and we hate that. So we want to cut off the tops of these oscillations, and we want to cut off the bottoms of these oscillations. So, for example, I live in the Rio Grande Valley, and the last big flood here was in the 1950s, and so the Middle Rio Grande Conservancy District built levees around the river to keep the river from flooding, and so that cut off the tops of the oscillations. And we're in a drought area, so we, over the decades, have built reservoirs upstream to cut off the bottoms. And so now we've managed to control these oscillations just a little bit. However, they're still there. I would argue that resilience and sustainability are really pretty closely connected. You can't have a sustainable system reaching long ways out into the future if it's not a resilient system, because it will crash and fail. And this is what we want engineered systems to look like. We won't want any kinds of oscillations in engineered systems. We know the grid certainly oscillates. However, we've been able to narrow the oscillations down to tiny fractions of a cycle of a hertz. So we've gotten pretty good at managing some of these engineered systems, but they still do oscillate, and that has to be tended to. So this is not resilient, not sustainable, and although this might look crazy, I mean, there's a lot of things in our lives that are like this, like human population on the planet Earth, human energy consumption on planet Earth is just continuing to trend upwards, and what goes up, So this is something to keep in mind. Here's what happens when systems are not resilient. And all of these things on the right are examples of the phenomena that occur when a system fails to be resilient, fails to rebound. And I think it's worth noting that most of these or all of these examples are relative. That is relative in time. So, for instance, we humans might wipe out 80 or 90% of species diversity on the planet, but given another 500 million years, that species diversity will probably evolve all over again. But to us, it'll look like a lack of resilience in species diversity in our shorter time frame. And so similarly with lots of these different topics there on the right, they're reasonably relative, but still very, very important to us on our relatively limited time frame. So what? Why does this matter? And I would say that we should anticipate oscillations in all of these systems. And we fail to. We want to straighten everything out. We work hard to straighten things out, but things are still going to oscillate. We should be observant of that. We should measure that. We should understand the rates of change, and we should recognize that these oscillations take place at many different scales. We should formulate long and short-term strategies and keep refining them. In ecology, back in the 90s, this term adaptive management came up, and it meant instead of applying a resource management plan and then just using it until it broke, apply a resource management plan and then constantly adapt it as you observe the system and see how the system is responding to the management strategies, then keep tweaking it as you go on through time. We need to, of course, evaluate costs associated with these failures and resilience, and eschew constant or exponential increase. And a pet peeve of mine is anticipate unintended consequences. Human history is littered with examples of unintended consequences associated with the things that we try to do. And we should be cognizant that those unintended consequences are going to occur either at the scale of our large-scale human decisions or even as individuals. And I'll say one more word about that a little bit later on. So now getting right into resilience, one could argue, I think fairly persuasively, that electric power is at the keystone of community resilience, community reliability. So when electric power goes out, the credit card machines go down, the gas pumps go down, water pumps go down, banking, public health, police and fire, all of that stuff can go down. And so electric power is crucial to maintaining resilience in a community. I'm going to talk about some formalisms associated with resilience now, spend a few slides talking about that. And, this might be, oh, there we go. Okay, so this is fairly obvious, but I'll just show that most outages to the grid supplied electricity are pretty short. So 50 minutes, 100 minutes, 150 minutes, and they get shorter and shorter as you move out in time. However, as you move out in time, the consequences of these outages go up. We've dealt with system reliability, as Masood was saying, but we don't often deal sufficiently with the concept of resilience. So there are a lot of folks now working on this subject, and here are the examples of some of the work that's come out of Sandia National Labs on the topic of resilience. And I put this up so you can, assuming that you'll have this presentation when we're all done. And if you're interested in this literature, you can go back and look for these documents. You can probably find them on the web. And if you can't find them, I can show them to you. Eric Bugren actually wrote the book on resilience. So there's an increasing literature on the topic aimed at trying to figure out how to make big systems resilient in a thoughtful, rigorous way. So these folks who are working on this have concluded that there are basically two approaches to creating resilience. One is attribute-based and one is performance-based. The attribute-based approach is more qualitative. It asks the question, what are the things that make my system more resilient, and do I have them, and if not, which ones do I want to add? And the performance-based approach is much more data-driven, much more quantitative, requiring modeling, requiring more people, and it explores how resilient is my system to different kinds of threats, different kinds of perturbations, how long can we expect systems to be down, and so on. And then, of course, how do we mitigate those problems? So these two different approaches are being applied. I'm going to talk about the performance-based systems, performance-based approaches, and I have an example of one. Oops, let me say this first. So here you see the oscillations that I talked about at the very beginning. Here's two systems, a little bit of a cartoon of a perturbation, system performance 1, system performance 2. The bold black line shows a system that crashed harder and longer, and that's less good, and we want to learn to mitigate those crashes and bring systems back up and running much more quickly. A couple thoughts about resilience. An important piece of resilience, I think, is that it's contextual. That is, when you're thinking about designing your system for resilience, it doesn't make economic sense in most cases to design your system to respond to every different kind of threat. You could do that if you have super critical infrastructure. So, for example, Sandia National Labs, some folks here work on nuclear weapons. There's a lot of critical infrastructure. There's a lot of security, a lot of resilience, a lot of redundancy, and it's really, really expensive. However, in most cases, it doesn't make sense to do all that, and you have to decide what are you going to build your system to be resilient to? Which threats are the ones that you want to address? And then you can address those at least, and it might make economic sense for you. So here's a bit of a formalism coming from this resilience literature. The first thing you need to do is define your resilience goals. As I just said, you pick what you're going to be resilient to, define the consequences and the metrics that you're concerned with, characterize the hazards. So how big are the floods? How big are the fires? How great is the drought? Determine the level of disruption that you want to be resilient to, collect data, build models, calculate the consequences of the different kinds of perturbations that you're expecting, and then evaluate your resilience improvements, those things that you're going to build into the system, and evaluate them using modeling to see if they obviate the issues that you're most concerned about. So if you're going to measure anything, you got to have metrics, and so the metrics that are being adopted for quantifying the consequences associated with these kinds of perturbations are here on the right side. The community metrics here's some examples: the numbers of people without services, the lives that will be put at risk, or the societal burden to reacquire the services when you need to rebuild it, put things back in place. Economic metrics are net economic losses measured in GDP or some other measurement, capital losses, the cost to rebuild a system, the business interruption cost. So what does it cost a system? What does it cost a business when it can't operate? You know, we're experiencing all of this right now with the pandemic and proving to be all that resilient right now. Security metrics. These are really important ones, and they're very, very difficult to place values on. The ability to serve critical missions like police, fire, rescue, communications for those rescue services. And one of the reasons it's so hard to value those is because it's hard to put a value on human life. And, you know, you might spend millions of dollars on a resilient system, or hundreds of millions of dollars on a resilient system, and you have to weigh that against what you might be saving. So 1 life, 2 lives, 10 lives, 100 lives. It's hard to put dollar values on those kinds of quantities. So here's an example of a project that Sandia implemented on resilience. So this is a big resilience study, and this is, you know, not something that every single municipality can do, but this is the way you would go about it, or this is the way Sandia went about it with the city of New Orleans. So you can see here in this box of all the different partners that were involved in this effort, and the question was, what keeps you up at night? And they decided in New Orleans that it was a high Category 2 or a low Category 3 hurricane with no mandatory evacuation. So this isn't the big it wasn't the big Category 4 hurricanes that they were concerned about. It was the smaller ones that for which they might not be adequately prepared. And so they addressed this question of what they can do about it. So just as an example of the very data intensive processes that you have to go through, these are some of the things that we did in New Orleans in order to put together this resilience plan. We needed to simulate hurricane tracks and try to imagine how often Category 4 hurricanes are expected to hit New Orleans. What are the maximum wind speeds associated with those hurricanes? What are our baseline outage estimations now, and how might those change over time? This page shows the critical assets that New Orleans needed to identify in order to go through this process. They needed to go through the city and pick out every single asset that they needed to be able to bring back up after some kind of big storm, and then this shows the different flood zones associated with those different critical assets. Some different levels of inundation, so there'd be different levels of damage, different levels of effort required in each of these zones in order to restore services. Then they had to come up with what are the measures that they would apply in order to restore the services in these places, and they simulated using microgrids, and the microgrid locations appear on the right. And then in the modeling that ensued, they evaluated the costs and the consequences associated with different microgrids in different areas, different combinations of microgrids, the expenses associated with different microgrids, and they kept doing that and iterated it over and over and over until they came up with a solution that they were satisfied with. And as far as I know, now they are working towards building in the measures that they hope will provide greater resilience. So this is a very formal approach to resilience, and this is something Sandia did. And you know, one thing that Sandia and all national labs have to do is get way out in front of commercial and industrial enterprises. That is, we can't be competing with business. It wouldn't be fair to take taxpayer dollars paid for by businesses and then compete against businesses. So we have to try to stay way out ahead in such a way that we're not competing. So this exercise was very expensive. And hopefully what will happen now is this kind of methodology will be passed on to commercial enterprises, and they can come to places like the state of Utah or any other place and use this methodology to evaluate ways of achieving greater resilience. So I think you might have seen this slide before. Either Dr. Gyuk put it up or Dan Borneo in the case studies talk put it up, but these are places where Sandia has collaborated with the Department of Energy, with the Energy Storage Program to build demonstration projects or small energy storage projects around the country. There's over 21 of them around the country right now, and there are more in the works that aren't on this map. And of these, here are the projects that were explicitly designed to address resiliency. So Sterling, which I'll talk about in a minute, backup power for police station. Green Mountain Power, backup power for emergency shelter. Backup power for emergency shelter. Backup for hospital. Backup for emergencies. So these are places where resilience was an important driver for the design and development of the system. But you know, last time I made a presentation like this, and Dr. Gyuk was listening, as I think he might be now, he pointed out that that energy storage addresses resiliency in every setting. Everywhere you put a big battery, everywhere you put energy storage, you are achieving greater resiliency in the grid because you're putting a buffer in between generation and consumption. And so if one side breaks, you have this buffer in place which creates resiliency. So when we are looking at resiliency, energy storage is a critical feature of any kind of approach to resiliency. So along with that go microgrids, which include other kinds of generation, and a very green kind of microgrid would include PV or wind and energy storage. So it's important to note that for a system, for a microgrid to be resilient, it's got to be able to be islanded. That is, it's got to function once the grid goes down. So I've got this PV system out in one of my fields, and it's a 6 kilowatt system, but it's grid tied. So when the grid goes down, my system's going to go down. My PV isn't going to do me any good at all. I would have to have a battery here at the house that the PV is charging, and then when the grid goes down, my battery has to kick in and provide electricity to the house. We don't have that. That technology exists now, and in fact, it's used all over the world in industrial, commercial, police and fire. People have it right now. Lots of folks have microgrids that are aimed at getting them through an outage. So here in New Mexico, near Albuquerque, we have a big Intel plant, and Intel has a big battery, And when the grid goes down, if the grid goes down, the battery kicks in milliseconds. And so there's barely a blip in the electrical supply to Intel. And the battery runs the electricity for a short period of time until the diesel generators kick in. Then the battery goes off and the diesel generators kick in, and the system is up and running with almost no interruption. So that's the old-fashioned way of dealing with resiliency. Of course, the batteries are kind of a new part, but there are downsides to that approach to resiliency. So the generators, the gas or diesel generators are noisy, and they're stinky, and they don't make great neighbors every place. You have to stockpile the fuel, keep it around. That can be expensive, and you have to maintain these systems. So when the big hurricane hit in Puerto Rico a couple of years ago, there were a lot of diesel generators hanging around that were supposed to kick in and solve the problem, and a lot of them had not been properly maintained, so they didn't work. So a lot of systems went down. Puerto Rico is like a poster child for resiliency and how important it is to be able to build resiliency and maintain resiliency when big storms come through. So let me go on. Some more general thoughts about resiliency. As I said earlier, you have to decide what resilience means to you in your community. What are you trying to be resilient to? And how are you going to plan that resilience? How are you going to plan for scheduled versus unscheduled outages? So in other words, you can manage your energy storage system in several ways. And I know that a bunch of you have been on these sessions all along, so you'll know exactly what I'm talking about. You can use your energy storage system. You can stack your benefits. You can use it day in and day out to accumulate revenues based on ancillary services and frequency regulation. But in that case, the state of charge in your battery is going up and down all the time, and you may not be ready to deal with an emergency. Your battery might not have the charge you need if something happens. The other way to deal with it is to plan for the crisis that you know is coming. And so in a minute, I'll talk about Sterling. Sterling, Massachusetts built a system in order to protect against winter storms. And they know when a winter storm is coming, and they can forecast it at least days in advance. And so when that's coming, they quit using their battery to provide ancillary services and frequency regulation and other things, and they just increase the state of charge in the battery. And then when the winter storm hits, they use the charge in the battery. If you don't know a crisis is coming, like an earthquake or a cyber attack or something else that you can't plan for, and if your battery isn't fully charged, then you simply can't use your battery to mitigate the problem. So with regards to valuing energy storage in the context of resilience, there are a lot of different, very conventional measures that have been figured out. The KD, KFI, SAIDI, the Customer Average Interruption Duration Index, and all of these others. These are all things that have been used in the engineering community and in the utilities and the electricity industry and other industries for a long time. You can look these up and you can see how they're used. More recently, Lawrence Berkeley National Lab and now others have used this value of lost load calculation to figure out how to put a value on resilience. But it's still tough because of that last line, public administration. That's one of the categories in the value of lost load calculation. And public administration includes police and fire. And we get back to that question of putting a value on the human lives or human health or response to rescues or potential damages from fire or other kinds of things. So here's the example that I think most of you have seen. I won't dwell on it. Sterling Municipal Light built their system to be resilient to hurricanes and ice storms. Those are things that you can predict. It's a relatively small system. It was mostly for fire and police. When it's fully charged, you can run it. They can run their police and fire for almost 17 days, and otherwise they're using it for all of these other revenue streams. The return is about $400K a year on an almost $3 million project. The return comes in. The system pays itself off after about 7 years, and their battery will last 12 years. And, you know, something I was thinking about that I don't know the answer to, maybe later on someone else from probably Dr. Gyuk will know. After 12 years, the battery may be not working in its optimal way anymore, so you can swap it out, but you don't have to swap out the entire project. You know, there's a lot of stuff that remains, but you have to replace the battery. And the battery, I don't know what percentage of the overall cost the battery may be, the whole battery pack. But anyway, it's not like replacing the entire project. So instead of replacing an entire $2.7 million project, you have less invested in the new project. And it's useful to point out that the DOE money and grant money help offset the upfront costs associated with this thing, which is, you know, relatively expensive. So let me change gears now. And talk about the resilience of energy storage. And so what I mean by that is we've concluded in a cultural way that continuing to burn fossil fuels is not a resilient strategy for meeting our energy needs. And we're turning to a whole bunch of different technologies: wind, PV, energy storage, and I personally am all for it, and I think it's absolutely the right way to go. But we have to ask ourselves how sustainable or how resilient is that approach. So these are 16 states that have adopted 100% decarbonization or renewable energy goals by 2040, 2050, 2030. There's also other states that have adopted lesser goals and other municipalities. And my own colleagues here at Sandia calculated what would it take in New Mexico to achieve New Mexico's 100% carbon-free goal. So let's start at the bottom of this list. Wind, we have 1.9 gigawatts, or about 40% of what we need. We need 5 gigawatts, and we need about 2.5 times more wind. We have a lot of wind down in the southeast, a lot of wind turbines down in the southeast, but in order to achieve these goals, and just based on all the assumptions built into the model that my colleagues used to come up with these calculations, all of which need review, they come to the conclusion that we need about 2.5 times more wind than we already have, and that's a reasonable amount. I can imagine that. We need about 12 times more PV. We obviously have a lot of PV in the state, increasing all the time. We need about 12 times more. I can imagine that too, but look how much more energy storage we need, 1,300 times more energy storage than we already have. That strikes me as a monumental increase in energy storage. And so the questions around all of this become, how do we do it? How do we do it in a thoughtful way? How do we achieve the goals we want to achieve in the time frames that we have? And what are going to be the unintended consequences of this effort to achieve all of these goals? Just to put a finer point on it, this Raccoon Mountain Pumped Hydro plant in Tennessee is a 1,600 megawatt plant, 22-hour duration. In order to recreate that in batteries, you would need, by just sort of back of the envelope calculation, 20 billion of these Tesla 18650 cells. These are roughly the size of a AA battery, 3 times the distance to the moon. So an enormous amount of battery energy storage is required to match the kind of energy storage that can be achieved via other means. But there's problems with all of these things. As we've talked about in other sessions, you can't go around building pumped hydro stations anywhere you want. There's all kinds of other problems associated with batteries. Now, we're putting all our stock, we're putting a lot of stock in batteries right now. And again, I'm all for it, but we have to be cognizant of the issues associated with the materials, say, that go into renewable energy systems and energy storage systems. On the left here, you see a list of the metals, some of which are relatively rare. difficult to come by. This picture on the right shows these percentage increases that are projected for light-duty passenger electric vehicles, energy storage capacity, installed PV. Now, anytime you take a number that's very small and make it very big and look at the percentage change, the percentage change outcome is going to be really, really big. And that's what's happening here. Right now, we have very few light-duty passenger EVs, but the number is expected to grow exponentially, very dramatically. And so as all of these things are helping us with our decarbonization problem, all of these things, we all see this now as the resilient, sustainable, reliable path to the future. But we mustn't be ignorant of all of the different sides to these equations. With regards to all of these metals, supply chain issues are one challenge. Rare earth elements are important parts of the generators in wind turbines and in other parts of the renewable energy storage universe. These rare earth elements aren't really rare, but they're widely distributed. They're expensive to get out. They're toxic. It's hard to substitute for any of them. China's a leading source. China's also a leading fabricator. We don't know how to recycle them yet. And so we're going down a path where we're going to need more and more and more of this stuff. So it behooves us to ask us how we're going to get it, where it's going to come from, what are we going to do with it when we're done with it. This is a graph coming out of a paper from about a year ago or maybe a little longer, showing that in order to meet projected demand in 2050 using PV and energy storage, we're going to need over 400% of the known cobalt reserves. And we're going to need over 250% of the known lithium reserves. So, no doubt there's more cobalt and more lithium in the world than we already know about. And no doubt there will be some kind of recycling and there will be other efficiencies. But we mustn't just blunder forward, not thinking about the challenges that might lie ahead. Other than supply chain bottlenecks, there are other things that arise with regards to all this stuff. Toxic mining, I mentioned, toxic post-consumer waste, insufficient life cycle assessment. Life cycle assessment, LCA, is studying all of the inputs that go into something. So all the water, all the energy, all the toxicity with regards to the entire life cycle of a product, from the time you dig it up out of the ground to the time you put it back into the ground. Child labor, cobalt, for example, has child labor problems. Energy inequity and injustice issues. Some of these are huge topics which require, many more presentations. Inadequate recycling, which is the case now for most of this stuff. Inadequate substitutes, need more R&D for all of that. And basically inadequate cradle-to-cradle design and production with regards to all of these different materials. Some people will say that transmission can solve the problem. I heard a guy from NREL recently say, we don't need batteries. All we need is more transmission, because, across the country, there's always energy being produced somewhere that can be used someplace else if we could just move it around. And maybe that's true. However, you got to ask, how are you going to move that energy around? That requires materials too. It requires transmission lines. It requires siting, jurisdiction, environmental reviews, costs, materials. And right now there are at least eight that I know of, big transmission projects that are on hold all around the country. That is, smart entrepreneurs have figured that have embarked on building these transmission projects, but can't finish them because of all the problems associated with building transmission projects. So a term that's coming up more and more now is the circular economy. I just got a paper yesterday from NREL talking about circular economy and recycling PV materials. So PV materials are interesting in that in the old PV panels, people don't even know what's in them. And so researchers are taking cores of PV panels and then analyzing the cores to find out what are all the metals that are down inside this depth of the PV panel. We have PV panels have a 20 or 30-year life, and then they go into the garbage, or they get recycled, or whatever. But right now, there is no robust recycling program. Wind turbine parts, similarly, no good recycling program. Lithium batteries, it's increasing. The recycling is increasing, but not that much is going on right now. And right now, lithium batteries make up 70, 80, 90% of the batteries that are being used out in the world, and they're projected to be the battery of choice for 5, 10, 15 years to come. So the linear economy is the economy we live in now. That means you take something out of the ground, you use it, and then you throw it away, and you put it back in the ground. And the circular economy, the idea of the circular economy is that things go round and round and round. You just keep reusing stuff. You design things so that they can be disassembled at the end, and all of the parts can be used again. And this is not such a new idea. The circular economy words are new. These guys, McDonough and Braungart, coined this phrase cradle to cradle 20 years ago. But anyway, it's gaining steam now, and that's a good thing. The circular economy does a lot of things. It reduces future extraction. It reduces waste streams. It reduces supply chain bottlenecks. It enhances resilience, sustainability, and reliability. And for some people, it's a national security issue with regards to certain kinds of materials. However, it's a really hard thing to achieve. It might be as hard to achieve a circular economy as it will be to build 1,300 times more energy storage in the state of New Mexico. It requires much greater ingenuity. It requires upfront costs. So it's going to cost a lot more to build a circular economy. However, you gain those externalized costs. You're accounting for the externalized costs that aren't now reflected in most of the costs that we assume these things require. So the circular economy is not a trivial thing, but it's probably a great thing to be working towards. So possible solution space. Let's sort of synthesize across all of this. Lithium ion is great right now. It might not be the long-term solution. Batteries may always provide short-term storage, like not seasonal, but maybe there will be other longer-term energy storage strategies that become more important for longer-term storage, which is going to be really important. Pumped hydro, compressed air, hydrogen, gravity, thermal. There's a lot of different technologies that you all have heard about over the course of this series. They all have their limitations. Transmission has its limitations. And it could be in the end that all of the above is going to be the solution space. Ralph and Hisham are going to talk about non-wires alternatives in a minute. That is deferring T&D construction and using batteries instead. High voltage DC transmission, cleaner batteries, new energy storage technologies, and all of these other things that you see in this list. It could be that in the end, it's going to be all of the above. And I'll end with just a little bit of an anecdote. I worked on water, energy, food modeling for 15 years at Sandia, and invariably we met stakeholder groups who felt that there was a silver bullet, that there was one technology that they could apply in whatever place they were in order to solve whatever resource scarcity issue they were facing. And in every case, there was no silver bullet. In every case, it took a mix of different technologies and approaches over different time frames in order to solve the problem. And so I have no reason to believe that it would be any different with regards to our energy demand. But in order to do that, we need to really understand all the inputs and outputs and consequences. I'll stop with this slide. You guys who heard me speak once before have heard this before. If you're in a shipwreck, a piano top comes floating by, you might grab a hold of it, use it as a life preserver. But if you were in the business of designing life preservers, you wouldn't build it in the shape of a piano top. We have fallen prey to that kind of dynamic in the course of human history countless times. We've got all kinds of things that we grasped onto to solve different kinds of problems. and they all had unintended consequences. And we should know by now that there are unintended consequences, and they're going to keep coming up, and we should be on the lookout for them in advance. I was in a futures group at Sandia for a while, and one of our premises in this group was that every institution ought to have a futures group. Every institution ought to apply 2 or 3 or 4 or 5 people or 10 or whatever to thinking about what's the future going to bring, how are we going to get there, and what are the strategies that we're going to apply, and what are going to be the unintended consequences of those strategies. So maybe that's a useful thing for us to consider as we move into this energy future. So this work of mine here today has been supported by my colleagues at Sandia National Labs, all of whom have contributed bits and pieces to this. And my appreciation goes to Dr. Gyuk, who manages the DOE Office of Electricity Energy Storage Program and who makes all of this possible for us at Sandia National Labs. Here's my contact information. Please don't hesitate to call or write. And I relinquish the balance of my time to the guys from Quanta Technologies. Thank you very much, everybody.
Well, thank you, Dr. Passell, for that presentation on energy storage and resilience. Moving on to our next presentation today, we have a presentation on energy storage as non-wires alternative to new generation and transmission/distribution. So I'd like to introduce Dr. Ralph Masiello, industry advisor and advisory services with Quanta Technology. Dr. Masiello chairs the U.S. Department of Energy Advisory Committee Storage Subcommittee from 2009 to 2014 and is a member of the National Academy of Engineering. His areas of expertise include utility automation and operations, ISO systems, processes, and market design, energy risk management, renewables integration into markets and operations, energy storage and distribution energy resources. He holds a Bachelor of Science, Master's of Science, and PhD in Electrical Engineering from the University of Massachusetts Institute of Technology and has over 40 years of experience in the electric power industry. I also have the pleasure of introducing Dr. Hisham Othman, Vice President of Transmission and Regulatory for Quanta Technology. His areas of expertise include power system dynamics and control, hybrid microgrids, grid integration of renewables and storage, economic analysis. He holds a PhD in electrical engineering from the University of Illinois, Urbana, and has over 30 years of technical and managerial experience in the electrical power industry. With that, I will turn it over to Dr. Masiello and Dr. Othman. Welcome.
Obligatory, who are we? Quanta Technology is a technical consulting company, part of Quanta Services. Quanta Services is the largest North American engineering and construction firm serving the electric and gas utility sector. We've had the introductions, so we can skip this slide. There we go. So if we look at the life cycle management of a storage project, the first step is the planning and the design. And if it's in the context of transmission and distribution planning, clearly integrated with those existing processes. The follow-on services, which we won't spend time on today, involve the steps shown on the box, which are normal for engineering and construction in infrastructure. And all of these are, let's say, in the developmental or pilot stage because storage is such a new technology. So for instance, testing, site acceptance tests, commissioning tests, tests to validate that safety rules have been followed, and ongoing operations and maintenance are still developing fields. We're going to cover some of the transmission and distribution applications of storage today. Not everything on the page because there's not sufficient time, but this simply identifies all of the potential applications and some on the left that are going to become more and more critical as we transit from conventional fossil-fired generation to any inverter-based renewable generation. We'll need synthetic governor response, synthetic inertial response. Those are sort of over the horizon. But we'll talk about storage in lieu of capacity expansion or reliability-driven investments in the transmission and distribution space. Okay, Howard touched on some of the barriers to storage adoption, and I think you've heard plenty through the seminar series on cost issues. In those states that have markets, California, New York, et cetera, there are relatively few market products designed around storage. Thanks to FERC 755, the regulation products have all been redesigned around storage. But the hourly energy, the real-time energy, and so on still reflect paradigms from conventional generation. NERC standards for reserves, for instance, have made it difficult for some cost-effective applications of storage. The technical issues that we'll focus on in this discussion are the models and methods in transmission and distribution planning. Utility transmission and distribution engineers do an awful lot of analytic work modeling the grid and looking at planning new construction alternatives, ways to address load growth or renewables integration. Most of the standard toolkits in use today, commercial toolkits, do not adequately represent storage. And if they do, they have a tough time keeping up with standard models for evolving storage technology. In front of this audience, I want to make an additional set of points that on the regulatory side, understanding the valuation, buying into it, and dealing with competing interests, presenting arguments about the value of storage can be pretty challenging today. And full disclosure, in a former life, I was one of the people in front of the California PUC talking about how to value storage. That was some time ago, but it's an ongoing problem. Another issue is today we fit storage in familiar buckets. We treat it as a generation asset or a transmission or a distribution asset or a customer asset. And in a lot of applications, that's correct. But increasingly, storage will become its own asset class and will need its own set of regulatory processes and rules and operational requirements that think of it that way. And if you think about the gas storage world, storage is a separate asset class when it's not storage in the pipe. And we know that for market monitoring, for instance, knowing how much gas is in storage is a critical question. That's not on the regulatory horizon today, whether it's California or at FERC, but in the future for the CAL-ISO, knowing how much energy is in storage and available will become a critical operational parameter. So with that, I think I'll turn this over to Dr. Offman, who will talk about energy storage planning in the transmission space.
Thanks, Ralph. Today I'd like to share with you some of our experiences as we were, we're helping utilities and developers in their pursuit of solving some of the issues or investments they need to make. Quite often, the context that we're working with, let's say a utility, is that they have either a reliability issue, they are not meeting some of the NERC TPL requirements, whether it's under N-1 or N-1 type situation, or you might have an issue related to market efficiency. Things are working, but there are congestions in the system they'd like to resolve. Or it could be related to some public policy issue where the state or the regulator is aiming to have a future, a high renewable future. They want to introduce offshore wind or more renewables in the system. And so now they want to design the transmission system to accommodate that, and what's the role of storage. Sometimes the context comes in as in the utility has designed a project to meet the requirements, a conventional project, and now they are looking to see if there is a non-wire alternative that can do the job technically, but at a cheaper price point. So those are the typical type of situations that we get, we encounter as we work with our customers. And invariably, the planning department of the utility struggles with introducing energy storage and studying it in a formal way where they can actually assure that it actually meets reliability requirements. So the issues of siting, optimally siting the storage, and then sizing it. And as we know, storage comes in, has two different attributes. It has the power rating and it has the energy rating. Invariably, utilities they can probably do an approximate job on siting and sizing the megawatt requirements, but when it gets to sizing the megawatt hour requirements, there's quite a bit of a struggle there. And that's based on all the studies that we've done over the last 5 years. We have built customized tools, if you wish, around the industry tools. So it's more productivity to enable us to do the job efficiently. And so the tools will help us to optimally size, site, but then the next level of analysis really is how do I compare this asset in a apple-to-apple comparison financially to a transmission or a conventional investment. As we know, those investments really have different asset management costs over time that's quite different. Storage, for example, it fades, it has a shorter lifetime. All of these aspects have to be taken into account as you're comparing them financially. And in addition, then you start looking at, there are attributes of storage and of lines that are really different. And one of them is more limited in energy, but it has more flexibility. So how do I extract and quantify? How do I attribute a dollar value to those? And for example, when you have a storage that is for reliability application, we all know reliability is not needed all the time. It might be attributed with, times of the year when the load is at peak or times of the year when the renewables are at peak. And for the rest of the time, it might actually be available to do something else, as in participating in wholesale markets. So that's one level of things. Another level is there's flexibility in how I apply. I don't need to design or plan the storage to meet my 20-year or 30-year requirements day one. I can design a smaller system to meet my 5-year requirements. And then as the load uncertainty or load forecast becomes more certain, I can actually expand it. So there are multiple elements that can come in here that we need to be, we need to have in order to properly plan solutions that involve non-wire alternatives such as energy storage. And it's not just energy storage. I mean, typically you need to look at energy storage, demand response, renewables, all of that as part of one mix. But today we're going to focus pretty much on energy storage and the use of it in transmission planning. Let me see if I can advance this slide. Ralph, can you push the advance because I don't have controls?
Okay.
Here. So as we said, the first thing is, does really energy storage help us really in meeting or in re reducing overloads or helping us with voltage issues on the transmission grid, and where to properly locate it. What's the optimal place to locate it? And it really depends on the context of the system that we're dealing with. So you need to have a way of properly siting it. And sometimes if it's a local issue, we end up with one site. Sometimes if it's a bigger issue, we might end up with 2 or 3 sites that we need energy storage to be coordinated at 2 or 3 sites in order to actually resolve the problem. Many times we find the optimal solution is not really just energy storage, but it's a hybrid solution that involves elements of reconductoring or upgrades or capacitors, whatever, in addition to energy storage. So that tends to be many times the most optimal and cost-effective solution. On the megawatt sizing, clearly we are sizing not only for the intact or the normal system, but it needs to be also taken into account all of these contingencies. And megawatt hour sizing needs to take the time element into account. So we end up actually needing to do time series power flow and time series contingency analysis, which is very, very time consuming, but that's the level that is needed, because sometimes just knowing I have an overload for 4 hours on this day, you might think I can design a 4-hour storage, but the problem is if that is a repeat, if it's part of a peak week and I don't have enough capacity in the grid to recharge the battery, then I need to actually oversize the battery in order to ride through the whole week. Next slide. So what I'm going to do now is just to make it more real is just to show you some of the case studies. So I'll take about 4 case studies, one targeted at grid reliability, another one at market efficiency. We'll go through a more elaborate one on offshore wind integration in New York, and then I'll talk about the real option valuation of energy storage and how exploiting the flexibility can actually help us to design even a more cost-effective solution. Next. So this first one is really on grid reliability, and we just chose one here where it's on the sub-transmission. We've done projects. You find the sub-transmission is right for these applications, especially on the edge of grid situations. But we've done projects on the 138 kV, we've done projects on the 230 kV, and even some projects on higher voltage than that. But this example here is in the MISO region, and it's with a large utility that has an issue not meeting the NERC reliability criteria. And the conventional solution would have required building a new transmission line that goes through some hilly terrain. That was deemed to be expensive, and they were looking for, is there a way to use energy storage to actually help us not build this extra line? And in this case, we've designed a battery that was 2.5 megawatts. And as you can see, we needed about 10 hours worth of storage in this case. And the cost of the battery, the initial cost, was much lower than the conventional solution. However, when you look at it on an apple-to-apple basis, as we went through the financial analysis, taking into account that the battery will have a calendar life of so and so many life cycles and augmentation and fading and all of that, it still ended up on a lifetime basis on a present value from a customer or a ratepayer point of view was about 2/3 the cost of the conventional solution. Now, so that's kind of the outcome of this exercise. Now, the more interesting thing really for planning engineers is that the tools that they need to actually do this type of analysis are still lacking, as Ralph mentioned. They can use ESSC, they can use, the traditional power flow solutions and contingency analysis, but the trying to really help them to optimally size it is still not there. And that's why we write a lot of productivity tools around those solutions. that enable us to do this time series type of state of charge optimization. Next slide. Now, this shows you some of the graphs that you would think this is dynamics, but it's not really. Here we're modeling, we're actually simulating the state of charge using time series bar flows. And so we practically will be simulating 8760 type snapshots, taking all the contingencies into account. And you will get graphs that help you really make sure that the state of charge doesn't dip below zero or stays within certain margin. And that, then you can design the megawatt hour requirement. So that's kind of the approach that we've used so far. But then we've kicked it a notch on the next slide, where we started looking at, if we have a storage, solar plus storage instead of just storage implemented, how can I use it for reliability? And quite interesting when you start thinking about storage, given all of the intermittency of the asset, of the harvest, and how can I really assure that I will have something I can rely on for grid reliability. And so this is kind of, I wouldn't say this is the mainstay of what we do, but it was an interesting exercise we went through, and we ended up doing a lot of probabilistic analysis because, you know, the load itself is variable, the solar is variable, and then how do they match and how do they align? That's also probabilistic. So we ended up doing quite a bit of Monte Carlo simulations around all of the reliability analysis. But the interesting part about it is you start now getting some statistical valuation for your reliability metrics. So in terms of line overloads and minimum bus voltages across the whole system, and where is the mean and low and high, and trying to design and optimize the relative size of the storage with the solar. Invariably, what we found is solar can help us reduce the megawatt hour requirements of the storage, even for reliability, but you have to really do a lot of analysis around it to assure that it will still meet your requirements. Next one. So now I'll shift to another example. This is offshore. This is in the UK, where we worked with National Grid looking at the boundaries between England and Scotland. Scotland has a lot of wind assets, and England definitely can use that energy. However, the boundary, 400 kV network there, is limited. I mean, thermal limits are okay, even if you go with intact on just looking at the and all that, it's fine. But once you start layering contingencies and trying to operate in a reliable fashion, then you start hitting limits. And those limits are causing them to spill wind in Scotland and operate more resources in England. So it's really a double whammy, and that's a market efficiency issue. And so the exercise or the project was to look at how can we utilize energy storage relative to conventional solutions. There are cost benefits to doing that. First, technically, is it okay? And then economically, does it work? So on the next slide, we start looking at the how much of boundary capacity expansion do we really need? Remember, the system will operate reliably, but it costs more today. So there is a level of expansion for this capacity of the boundary where it kind of becomes the most optimal. If I go beyond it, yes, it's more capacity, but I don't need it. If I go below it, then I'm paying more for the spilled energy and the thermal energy running in England than the cost of the project. We figured a certain size where it's the most optimal expansion size, about 2,300 megawatts that we needed to expand the boundary with. And that's when we start working on different solutions to get to that level. So on the next slide, we looked at conventional solutions. We looked at solutions that involve, its hybrid solution involves some elements of conventional and battery storage. And we ended up actually, when we look at it, apple-to-apple comparison over the life, we ended up with solutions that range between 48% to 88% of the cost of the conventional alone. So it was actually quite interesting, even at 400 kV for market efficiency. You could find good applications if you have the proper tools and the proper process of analysis. And of course, the system lends itself. I have to just say a word of caution. Not every project that we get, we find that storage is the best. And actually, if anything, it's the other way around. We find probably maybe 30% of the situations we're invited to analyze where storage is actually the optimal way to go. Many times it's the just conventional solutions would be far more cost effective. Next one, I'll just go through an example here back in the US looking at policy issues. Here in the state of New York, they have a policy of integrating 9 gigawatts of offshore wind into the zones J and K, basically in Long Island and New York City. And as you can imagine, the grid was never really designed to bring energy from the ocean into the into the grid. So now this is really trying to bring in something in a totally unplanned grid and see how we can integrate it. The first thing we looked at is, okay, how much can I really integrate in steps, and what sort of impacts do I have on the grid? And so part of it is trying to figure out where do you want to interconnect this offshore wind, what we call POIs, points of interconnection. And of course, the developers for the wind might go in different directions, but in this exercise, we try to see if there's a coordinated planning and we were to optimize those POI allocations to be the most, the ones that will cause the least grid issues. So when we integrated 3 gigawatts, we found 7 issues, some of them on the 138, some of them on 345. When we integrated 6 gigawatts, the issues grew, more violations in the grid. And when we go to 9 gigawatts, it even grew more. So for this exercise, we focused on the middle scenario of integrating 6 gigawatts and wanted to see if we were to do it conventionally and if we were to use energy storage, what would be the outcome. On the next slide, just before I talk about this, we looked at the conventional solution. We figured we need about $1 billion worth of investment at minimum, not taking into account all the permitting and some of the difficulties of actually upgrading some of those 345 kV underground cables. So just taking it at face value could probably be about slightly over $1 billion. So that's really the bogey we're competing against. First thing we do is we try to look at optimal locations, and our methodology will basically take all the buses in the study area and will attribute a score to them as to their effectiveness. And then we pick the ones where we think there is space in the substation or nearby where we can actually build storage. So those are basically candidate sites. And then we go on to the next slide and we start looking at where are these locations. So we start looking at megawatt sizing. This is the megawatt sizing, taking all the contingencies into account that New York ISO will consider. We ended up with 3 sites. 2 of them are in discharge mode, and 1 of them, the green one, in a charging mode. We actually needed 3 storage systems working in a coordinated manner, 2 in discharge mode, 1 in a charging mode, to alleviate all of these constraints or the violations that we had in the grid. So to enable 6 gigawatts of offshore wind to integrate, we actually, in this case, we used a pure model of just energy storage, but we needed 3 of them, totaling about 158 megawatt storage. In today's market, 158 is not really is not prohibitive anymore. If we were talking 5 years ago, 100 megawatt was too large, but in today's industry, we've broken those records some time ago. So 158 looks very reasonable, but we don't know how many megawatt hours to really figure out the cost. So we go on to the next slide. And we start looking at this one here. We start looking at, can I hybridize it? Can I address some of these constraints using conventional solutions and others using storage? And the tool will help us actually. It will start peeling the onion, basically. If you look on the table on the upper right, it says if you address nothing conventional, you need 157 point something, which is the 158 megawatts. However, if you start addressing some of those lines conventionally, then the storage size will start dropping. I'll go on to the next slide just to give you the upshot. When we did the 8760 optimization or the time series, we ended up with a storage size that was about 9 hours of storage. It got optimized completely at about 126 MVA, 1043 megawatt hour storage. So that, we go to the next slide. We looked at the cost for that storage was about $310 million. So relative to the $1 billion on a first cost basis, it looks very attractive. Then we start looking at it on the next slide on the lifetime basis. No, I'm sorry, the previous one, right? And on the, when we look at on this level, we found the cost of the storage to be about 65%. We actually do the cost apple to apple in two different ways. One of them is we look at it over the life of the conventional asset. The other one, we look at it over the life of the storage asset. And we take a slice, basically a levelized real cost of the conventional, and we compare them. We see the cost or the comparison is 65% to 98%. So it's still in the still attractive to look at, especially if we think about the permitting and the difficulty and the interruptions we need to go through if we were to go with conventional solutions. So it seems like it could be an interesting application actually for the states on the East Coast as they are looking at offshore wind integration. The next one, this is the last slide I will talk about before I move on with to talk about distribution. Here we're looking at real option analysis. This is actually a project that we did in California with a large utility. And after we studied the conventional and we analyzed the storage solutions, it was an area of the about 110 to 138 kV part of their system that they needed they had several violations, and we ended up designing a hybrid solution for it that involved one upgrade and a storage system. Now, the conventional solution itself was $60 million. The energy storage system without any market participation was actually more expensive, was $70. However, when we looked at the reliability needs, we figured we can actually use the storage in the market, and that brought down the lifetime cost to $50 million. So it's somewhere close to where the conventional. Now, the next level we studied is, as we designed the conventional and the storage, that was built on a certain load forecast. Where is my peak load going? And there is quite a bit of uncertainty in how the load is going to develop in the future. So we looked at that load forecast uncertainty, and we also looked at the market prices and ancillary prices that we used in the revenue stacking as also another uncertain. And we used those through a Monte Carlo simulation where the x-axis, we're looking at the relative cost of storage to conventional. So that's the cost ratio. Anything below 100%, the storage solution is cheaper. Anything above, the storage solution is more expensive. And from all the samples we looked at, we see that the storage on a mean level was 73% of the cost of the conventional. So it was actually more economic. However, there are some times when the cost of the storage was higher than 100% of the conventional. And those we found them to be about 3% of all the scenarios. So using storage where we can actually design it, where we build only 5 years worth of needs, and then look at the load forecast, figure out if I still need to upgrade further, which is what we did in this example. And we use that type of methodology to design or plan the storage solution versus a conventional where I need to build it weather the, based on my worst condition. So this is another way of analyzing energy storage and their needs. With that, I'll turn it back to Ralph.
Good. I'll talk about distribution applications, which are day in, day out kind of things, and not necessarily as exciting as some of the things Hisham presents. And I'll talk about capacity deferral and PV integration and reliability. And also about the puzzle of not looking at particular cases, but looking at the entire system. How do we build a roadmap of how storage might be deployed across all of the stations and circuits in the system over time? Where are the sweet spots technically and financially? Hisham showed a block diagram of the process and the tool. Same block diagram almost for the distribution space, except the standard products for planning have different names in distribution: SIME, Synergy, MillSoft, EPRI Open, DSS, etc. And the possibility exists to do a system-wide evaluation. But the concepts, the mathematics, the cost-benefit especially, are very nearly the same. Good. Now, Hisham talked a lot about 8760, and I want to come to that and explain why it's so important. Because today in the distribution world, we study the peak day and hour, or several peak days and hours, and increasingly we study a Sunday afternoon in May or September because we're looking at periods of high PV production and low load for renewables integration. When we start talking about storage, and increasingly with high renewables penetration, we have to do the same thing in distribution as is commonplace in wholesale transmission, which is to look at the every hour in the year, thus the term 8760. And this is a simple example of why is it important. If we look at a distribution circuit with a load profile on the left, and you can see that it's forecast to go over the rating 2 years out, and we need to do something to add capacity. If we are going to look at storage for deferral, the important question is, am I deferring that capacity 1 year, 3 years, 5 years? How long can I leave the storage there? And if we had a load growth forecast year over year, the peak load would go up linearly with time. But the size of the battery is the area under the curve. And as we move the curve up, the area increases quadratically with time. So when we look at the cost effectiveness for deferral, we're in a kind of race. The longer you can defer the station expansion, say, the longer you've got savings and the better the net present value of the savings. But the longer you do the deferral, the bigger the battery has to get and the costs go up. And the battery size goes up, so the costs go up. But over time, the battery costs per megawatt hour may come down. So there's an interesting but complex race time-wise in doing this analysis. And that comes up in every application. So my first case study is one of my favorites because it is high profile and exciting and very recent. In Washington, D.C., PEPCO, Potomac Electric Power, forecast a lot of load growth in the corner of the city behind Union Station, if you know the district at all. And that's an area that today is changing from old warehouses mostly to upscale office buildings and some residential. A lot of construction going on. And the existing underground network wasn't sufficient to handle the growth. And they're spending close to $1 billion to add 230 kV subtransmission. Yes, in Washington, D.C., 230 kV is subtransmission, and a new substation to serve that area. And the stakeholders, who were many, came and argued that they could avoid building that substation and use batteries. And it took almost 9 months of work analyzing all the potential contingencies around those underground networks and against the possible load growth, and looking at scenarios of increased photovoltaic, for instance, or batteries with smart charging, to finally convince the Commission that deferral using storage was simply not viable under any condition. First, it wasn't viable in terms of the size of the batteries needed and the costs. Second, it was also going to be not viable in how do you locate 20, 40-foot containers in downtown Washington with batteries. And it also wrapped around safety issues of, is it realistic to put a battery in a parking garage or a school park? So this is a great example of what Hisham said. Storage doesn't always work. We're passionate about storage. We believe in it, but it's not a panacea. Okay, this one is sort of from the sublime to the ridiculous, and may actually be germane out here, out west. I should add, I'm a neighbor. I live in Carson City, Nevada. This was a case study in upstate New York, up the Hudson River in the Adirondacks, and a circuit fed a ski lift. Pretty much the only load on the circuit was a ski resort, and building a new ski run and building a new lift was going to increase the load a lot, and this created the potential for a very expensive additional circuit. And it turned out in this case, putting a battery there to peak shave and avoid the need for that second circuit was cost effective. Okay, so this is a PV integration example. At high PV penetration, we see 2 and perhaps 3 engineering problems. The first one is the photovoltaic fluctuates and it can cause too much flicker on the circuit. The circuit voltage rate of change can exceed ANSI standard, and if it's too much, we get flicker, which means the customers see the lights down. The conventional fixes for that can be expensive. It means, quote, stiffening the circuit, increasing the conductor size to decrease the resistance and the sensitivity of voltage to the PV production. A very small battery located with the PV can be used to change the rate of change. So if you look on the bottom graph, you can see the storage just slows down the changes that occur with the photovoltaic fluctuation. It doesn't take a big battery. And in fact, it's a potential incentive mechanism to say to big PV installations, if you'll put in a small battery and a smart inverter and do this with local control, you avoid the flicker problem for us, save us money. So it's kind of an interesting application. If we look at reliability, in distribution reliability, the issue is shown on the upper left. The third section of the circuit may be isolated if there's a fault upstream. And if there's a circuit up a mountain pass or out a peninsula into a body of water, or sometimes in the edge of a service territory, getting an additional circuit with enough rollover capacity may be very expensive. So just as with the example shown on transmission congestion, you don't need a perfect solution. There's a sweet spot that says, how much of those outages in the lower left-hand curve do I want to cover with a battery? And the utility could say, on average, we can recover an outage on that circuit in 6 hours. Some of them may take 24 hours, but they have been very rare historically. The 6-hour battery is the best solution. And so that can all be analyzed statistically and with the engineering. And if the utility is in a market environment, then during those times of the year, when not all the battery size has to be held in reserve, it's possible to make use of it doing energy arbitrage or providing ancillaries. You heard a lot from Ray Byrne about stacked applications and market benefits. So I won't go into the details of how you look at a battery providing regulation service. But I'll add two comments. Sandia and EPRI both have excellent tools publicly available for analyzing batteries in the markets. The trick when you look at stacked applications, market participation, on top of T&D applications is you've got to consider the T&D reliability need first. So if we need that battery for peak shaving, that's a constraint. And that constraint will vary from circuit to circuit. So in order to analyze that, you've got to be integrated software-wise with the utilities planning software. And it makes it tough for a standard publicly available piece of software to do that, as well as issues about cybersecurity and can you move your circuit models up to the cloud and so on. But in the West, if you're not actually in the CAL-ISO, the imbalance market is an opportunity for market participation, and storage can be very economical in the imbalance space. This looks complicated, but it really isn't. This is just showing the economics of deferral. Here in the upper right, the gray graph would be in year one, we upgrade the distribution circuit, we reconductor. So we spend a bunch of money in year one, and then we'll spend, we'll see a variety of things going on year after that, depreciation, operating expense, et cetera. And if we instead defer it, we have the green graph that says years 1, 2, and 3, we spend something on a battery. And then in year 4, we go do the classic investment anyhow and spend more money. And so the financial cost benefit is the net present value of the difference of those two curves. And depending on how many years of deferral, it'll be positive or minus. And down at the bottom, you see each row is years of deferral, and red or green says, does it work or doesn't? And the different labeled columns are basically, are you just using the battery for peak shaving? Are you also using it for time shifting hourly energy? And are you also providing ancillaries? And it shows in this case that the 3-year, I think, is the best. So if we have to look at the entire system, for a big utility, there could be 5,000 circuits, maybe 500 stations, 5,000 circuits. Doing this kind of analysis on every circuit is pretty tedious and unnecessary. And so a good process is to develop screening parameters that look at critical issues. And what's the rate of load growth? What's the spare capacity on the circuit today? What's the customer mix, which shapes the profile? And screen the population against those parameters, mapping each circuit to one of a couple of dozen that were analyzed in detail and adjusting it for how the parameters changed, and build out a plan for storage over time. And that could enable a utility to make a very good financial case that says, we don't need 2,000 megawatts of storage. We're going to need 1,750, and here's why, and here's how it plays out over time. And then another little complexity that comes into play when you look at a storage roadmap over the years. If you put the battery out on the circuit or in the station to get 3 years of deferral, what do you do in year 4? If the battery had been hastily deployed, as was the case in California right after the mandate, they picked locations primarily based on siting, ease of siting. But if you are doing it intelligently, you say, I don't want to write that battery off after 3 years. So I'll look at the economics of spending a little bit more up front to make it removable so that I can relocate it to the next problem. Especially in a market environment, you can say, at the end of the deferral period, I'll leave it there and I'll just use it for market applications. And so that, those are twists on the problem that let you improve the economics. Okay, so state of the art, especially in the distribution space, the standard planning tools today can't do these kinds of analyses. So we need, let's call them semi-custom tools, as we've illustrated. But over time, those standard tools will absolutely adapt to be able to deal with storage in a completely high-fidelity way. Some areas of ongoing research and that are very important in these economics. How does storage degrade as it's used? And this is a function of how many discharge cycles, what are the statistics on how deep the discharge is, potentially with some technologies, what's the rate of discharge? And why does this matter financially? The utility, whether it's doing a purchase power agreement or investing in the asset, wants a multi-year warranty on the storage system against failures and against degradation beyond the forecast. And if the warranty is strictly written, the manufacturer simply configures the extra capacity to fulfill the warranty. And that could double or more the amount of battery size, and it increases the costs. So when you read some public study by any of the market research companies, and they tell you batteries are $230 a kilowatt hour today, and they're coming down, and they'll be $150 in 2 years, and then a utility goes out for a procurement, and back come the prices of $1,000. It's not that the manufacturers are gouging, it's the issues around the warranty terms and the forecasted use of that battery over time. And ultimately, the negotiation will be coming around, you get to discharge it once a day, and you'll never discharge it below 40%, requirements like that. So that's an area of active and very important research. So we've covered a number of applications out of many. Happy to come back and talk about others, such as volt-var management or stability enhancement. We've got examples where batteries have been looked at on the transmission system to provide transient stability, for instance. And that's a common problem in South America and in the... So I think with that, we have a few minutes for questions and answers. Kevin, back to you.
Yes, thank you, Dr. Masiello and Dr. Othman for that presentation. So yes, we have a few minutes left for questions. So with that, I invite those of you who have questions to unmute yourself and ask, or feel free to send them to me in the chat and I can ask on your behalf.
Okay.
All right. Well, I'm not hearing any questions at this point from our attendees. I myself actually have a question for the speakers today, since we have cricket. I was reading an article that a colleague of mine shared with me, and it was in regards to the British grid and grid balancing that is going on over there as a response to COVID-19 and fluctuations and reductions in the overall demand for energy with the shift in people working from home and just scaling back in general, just while sheltering in place. And they're looking at spending over £500 million to help shift and reduce demand to prevent rolling blackouts. Now, at what point, and how does energy storage kind of compete in that regards to an issue like resiliency and kind of competing a pandemic like we're experiencing right now?
Hisham, I'll take a stab. If the demand profile is shifting, storage can help, for instance, if the profile doesn't align with the wind production profile as well. Most renewables in the UK are North Sea wind and Northern Scotland wind. And so if the demand profile looks different, it may not match as well. It's a very different environment than the US, you know. I can remember 30 years ago sitting in the control center there and watching the sudden dip in demand at tea time. Spike at tea time as everybody turned on their teapots. So that's one. A second issue that we'd certainly see in the U.S. is the location of where the peak load is going to change. In other words, Con Ed in New York, for instance, the peak is in Manhattan. But if people are staying home and working from home, the peak could shift to Brooklyn and Staten Island. And so that creates issues that circuits, which were not heavily loaded during the day, are now heavily loaded because everybody's home and they've got the air conditioner on where they would have been set back and so forth. And storage can help with the peak shaving, obviously, in that case. Okay.
Well, thank you, Dr. Masiello. Any other questions at this time? All right. Well, with that, I would just like to say thank you for those of you for attending the State of Utah Energy Storage Summer Webinar Series. Has been presented by the Department of Energy Office of Electricity Energy Storage Program in collaboration with the Utah Governor's Office of Energy Development, Sandia National Laboratories, Pacific Northwest National Laboratories, Mustang Prairie Energy, Quanta Technology, and the University of Utah's Utah Smart Energy Laboratory. A special thanks to Dr. Gyuk and the Department of Energy's Office of Electricity Energy Storage Program for sponsoring this webinar series. I'd like to thank today's speakers for participating and providing us just great information on energy storage and resilience. And I would like to thank all of you again for attending. And for questions about the series, copies of the presentations, and information about the recorded sessions, please reach out and contact myself, Kevin Brooks, at the Governor's Office of Energy Development, and that can be found at kevinbrooks@utah.gov. And with that, any last words, Dr. Gyuk? Again, thank you very much for supporting this series. It has been wonderful to work with all of our partners in putting this together.
Well, it's my pleasure to have participated in this series. It's not only that Congress wants us to do it, but it's important for us to know what the problems and the interests are state by state, because this is a large country and we want everyone to participate in the future of energy development. So thank you for your participation, and it's been a pleasure.
Excellent. Well, thank you, everyone. Have a wonderful day.
Thank you.